Okay, so recapping from yesterday, we are going to do cross sections with different shapes, and we developed the formula for an equilateral triangle. I mean, technically, we can now do these kind of shape things with any shape. They could give you an isosceles triangle, and you just have to figure out what is the area of the cross section, and then that area goes into your integral from A to B. So let's look at an example. Here's our same x squared and square root of x graph that we've done. That's the base, and the triangles would be coming outside from that. So you'd imagine taking a cross section, again, perpendicular to the x-axis, tells us our cross section is this way. And if I took that little red thing out and turned it sideways, it would be a perfect equilateral triangle. The area of that triangle was root 3 over 4 s squared, and this length right there will be our top graph, which is the square root of x, minus our bottom graph, which is x squared. So that's going to be your side length. That gets squared. Just cheat and use your calculator for now. But if you had to do it by hand, it wouldn't have been bad. What's the only thing I'd worry if you were doing it by hand? Right? When you square that, you'd have to FOIL that out, right? Just have to be careful that you don't just square the first and the second term. Actually multiply that all out. So now we could do these questions. Any kind of curves could form the base, and you could do it with equilateral triangles. Good. Next. What if they just make it an isosceles right triangle? What makes something a right triangle? A 90 degree. Isosceles means this side and this side are the same length, which would make those other angles 45 degrees. And here you could just use 1/2 base times height for your triangle, which ends up just being 1/2 s squared. So on all of these cross sections questions, where they tell you that the area bounded by the curves is the base, and the cross sections are a different shape, you have to figure out the area of that shape based on, I'll erase that s, because this s is your cross section. And then all of the other information, like this one was isosceles, so that told us this other one was an s as well. And it doesn't matter what letter you would use in that situation. So here's our same question. Cross sections perpendicular to the x-axis. We draw a cross section. And I would suggest whenever they say perpendicular to actually draw that line in to tell yourself if it's a dx question or a dy question. Same thing, fairly straightforward. And our last idea, we're going to look at the same one, but we're going to use semicircles. You know the area of a full circle is pi r squared. And so half of a circle would be half pi r squared. And the radius goes from here to here. But this whole length, if this is the cross section, this whole length would be the one function subtract the other function. So does it make sense that our radius would be f of x minus g of x cut in half? So again, perpendicular to the x-axis, draw our cross section. This time it's a semicircle. So we would have the square root of x minus x squared is the length of that red line. You would have to cut that in half. So I'm going to draw a green dot on there, and I'm going to take that little slice and cut it out for you. Can you imagine slicing that, pulling that one slice out, turning it sideways and putting it here? That green dot is the same as that green dot. That red line is the same as that red line. But now I can see the semicircle coming out of the paper. That semicircle would come out towards you. You need that 3D graphing. But this is good for your mind to see if you can visualize that. So then my radius is going to be half of this one minus this one. Right? The area of a semicircle is 1/2 pi r squared. Right? So we're really figuring out 0 to 1 of 1/2 pi r squared dx. That's what should be in your mind. And then it's just a matter of, okay, what is my actual radius? It's just f of x minus g of x cut in half. If I wanted to, I could simplify this a bit. I squared the bottom and I left the top in brackets squared. Pi times 1/2 is pi over 2. Again, when typing things into my calculator, I like to pull out the pi over 8, especially the pi. I like to pull out my constants, just in case what we plug in is a nice answer. So we're going to just look at that with our calculator right now. I'm going to go scroll up so you can still write that in. I'm going to go to math. Maybe. Yes, it's coming. Hit the math button. Go down to number 9. No. My calculator is not responding. There we go. There it is. We're going to go from 0 to 1, bracket, square root of x minus x squared, bracket squared, dx. So notice that your calculator adds an extra set of brackets around the whole thing. So just as far as looking at what I typed in and looking what's actually there, making sure that that matches up. Okay. Now when I push enter to this, I get a decimal. I might see if that could change to a fraction. It does not. That's not necessarily to say it can't change to a fraction. It's just the calculator might be lazy at this moment in figuring things out. So then I could then times this by pi over 8 and get our answer to 3 decimal places. 0.050. Okay? But what might have been nice is if that answer was a perfect fraction, then I could leave my answer as an exact value. I can multiply it and have it say it's like 32 pi over 17 or something. And our very, very last question. Solid has a circular base of radius 4 centimeters. Find the volume of a solid if every plane cross-section, so plane cross-section means that you're kiting it straight up and down, perpendicular to a fixed diameter, is an equilateral triangle. Here's our base, right? A solid has a circular base with a radius of 4 centimeters. Every cross-section that is perpendicular to a fixed diameter. And the reason they have this fixed diameter is there's a bunch of different diameters in a circle. There's lots of them, actually. They say, let's just make one of them. It could be this one. It could be diagonal. Could be anywhere. But fix one of them. And I fixed it as a horizontal line because that's going to be easier for us to think about. So now, if I take a cross-section perpendicular to the fixed diameter, this would be my cross-section. And this cross-section, if I pull it out, makes an equilateral triangle. First of all, do you know the equation of a circle? If I told you that this happens to be 0, 0, could you write the equation of that circle? Okay? And the equation of a circle goes back to grade 12 pre-calculus, the unit circle. The unit circle, you learned that sine squared plus cos squared equals 1. You learned that cos was always your x coordinate, sine was always your y coordinate. Basically, the equation of a circle is just a squared plus b squared equals c squared. Any point that I pick on here makes a right angle triangle with an x coordinate and a y coordinate, and because the radius is 4, the hypotenuse of that triangle would always be 4. And so we just take that triangle and say, well, it's definitely true that a squared plus b squared equals c squared. So this is the equation of a circle. If you got y by itself, technically you would get a plus or minus there when you square root both sides and get y by itself. But if we think about only the top part, we would have a graph like this, and the bottom part would be the negative. So how am I going to set up my integral to count up all of these areas? One thing I could do is I could look at going from 0 to 4 and look at, what did we do here? This looks like setting up my equilateral triangles from 0 to 4, because I've got my root 3 over 4. That's my area of my equilateral triangle. But another thing you could think about on this one is you could also go from -4 to 4 and just do half of it. If I did half of it, can you see that it would make half of your equilateral triangle? So if I go from -4 to 4, and that would give me half of my equilateral triangle. And then double this, I would get the full equilateral triangle. Different ways of thinking of the same thing.
Okay, so